Okay, so we talk about more on RSA, like so we have seen the RSA crypto system. So here Alice and Bob is communicating, and Bob is doing this setup, key generation or the setup, because Bob has to get the Bob's public key, and because Alice wants to send a message to Bob. So Bob has to, Alice need to get Bob's public key. So that Bob can only do this setup in order to get the Bob public key private key pair. So for this setup we need to have, say, Bob has to choose 2 prime number P and Q, such that 2 prime number P and Q, then Bob, so these 2 primes, so Bob has to choose, then Bob compute P into Q, okay, and then Bob choose then Bob compute phi n, which is Euler phi function, and then Bob choose a E, which is basically GCD of, which is basically co-prime with phi n, in order to have the inverse. So that means you will have the inverse, that is called D. So ED is congruent to 1 mod phi n. So D is basically E inverse mod phi n. So this inverse exists because we have this condition, they are relatively prime. So this is the key generation phase. So Bob has to do this key generation, and then Bob make D to be pivot, sorry, D, and the public key is basically D and PQ. PQ also be pivot, and public key is basically in and E, and this will be sent to Alice or anybody else who wants to send a message to Bob. So suppose Alice wants to send a message to Bob, so Alice will receive Bob public key. So now Alice will compute, so m to the power, so this is the ciphertext, m to the power E mod n, okay, and also then this is the encryption, and for decryption what Bob will do, Bob will compute y to the power D mod n. So this will give us m. Yes, we have correctness, we have seen. So this is the RSA crypto system. So we today in this talk we will talk about some computational aspect on RSA and the security aspect on RSA. So let us start with the computational aspect of RSA. So the complexity of the computation requires 2 steps, like for actual encryption and decryption. So we have seen that for encryption we need to do the m to the power E, so that exponentials and how we can calculate, and for decryption also Bob has to calculate y to the power sorry, for encryption m to the power E, and for decryption Bob has to calculate, yeah, so for encryption m to the power E. So how one can calculate this? So m may be some large number, say 191, so E may be some another number, say 9, so mod something, some large number. So how to calculate this type of exponentiation? So this is in encryption as well as for decryption also what Bob is doing, because this is a number. So this is 5 1 1 2 3, say for example, and say D is some number, say 4 1 1 6 9 7 mod something. So this is one aspect of computation complexity, how one can calculate such exponentiation. So that we have to handle. And another issue is, so we need the primes, so PQ. So how to get the primes PQ? So is there any algorithm who can give us the prime PQ? So the prime numbers, so that is the key generation step. So these two are basically computational aspect of RSA. Now for encryption, so exponentiation we need to do. So basically we need to compute some a to the power, okay, or x to the power some power, something like that. So both involve some large. So these are under modular operation. So under modular operation we can use this this fact that a mod n into b mod n, then mod n is equal to a into b mod n, okay. So, now suppose, so for RSA we need to do the exponentiation. So, suppose we want to calculate the x to the power 16. Okay. Okay, so suppose we want to calculate x to the power 16. So, x to the power 16 is basically x into x 16 times or say 15 times. Okay, so this if we need to calculate say x to the power e or say x to the power m, okay, or say x to the power n. So, this is a naive approach. So, this will take order of n times, I mean like, so n multiplication, if it is x to the power n like this. So, how we can have a efficient computation for this exponentiation. So, that is one challenge in RSA. So, for that finding x to the power 16, what we can do? We can just calculate x square, then again x square into x square. So, x to the power 8, then x to the power 4, then x to the power 8, like this we can do. So, this is called this technique we will use in what is called square and multiply method. So, more general, suppose we want to find a to the power m. So, a, b are two positive integer. So, now we express m in a binary form. So, like this. So, suppose we want to calculate a to the power m. So, where m and a and n are two positive integers. Now, we express m is in binary, say bk minus 1 up to b0, k bit binary bit. Okay. So, now m will be written as what? M will be written as b0 plus b1 2 plus b2 2 square, like this. That means bk 2 to the power k. Okay, this is in decimal integer, m integer. So, so to get the binary form, we have to keep on divide by 2. So, we got b0, then we again divides by 2 on the remainder, like this. We have to do like this. So, this is basically we can denote by sum of the bi 2 to the power I is equal to 0 to k. Okay. So, now we are calculating a to the power m. So, a to the power m is basically so this we can just write a to the power. So, summation of bi. So, this we can write just summation of 2 to the power I, where bi is not equal to 0. So, 2 to the power I, where bi is not equal to 0, that is it. So, this is basically, so this sum will take the product form. So, a to the power 2 to the power I. So, this bi is not equal to 0, where bi is not equal to 0. So, every time we will square it, and once the bi is not 0, we will multiply. So, this is called square and multiply. So, this will give us this expression like this. So, if m is this, then a to the power mi is basically in this form, then this is basically product form a to the power 2i. So, every time we square it, so a to the power 2i. So, this is basically mod m is basically in this form. So, this is called square and multiply method, square and multiply algorithm. So, this we will write in a pseudo code like this. So, we start with z is equal to 1, z is the our a to the power m. Okay. So, now we start with that bk. So, this is bk down to 0. Now, every time we square the z. So, z is equal to z square mod n, and if the bi is 1, then only we multiply with a. So, if bi is 1, then only z is equal to z into a mod n. So, every time we are squaring, only we will multiply when bi is equal to 1. Okay. So, here is an example. So, if you take n is equal to say some value 1 1 4 1 3, this is n, and if you take m is equal to 3 5 3 3 and a is equal to 9726, and suppose we want to compute a to the power n, 9726 to the power 3533 mod 11413 using the square and multiply method we have seen. So, we write this m into binary form. So, this is the binary representation from this is from B0 to B11, okay. And then we call this algorithm, we start from B11, and every time we square we start with z is equal to 1, every time we square whenever we see a 1 in Bi we multiply. So, this z is basically 1. Now, this is 1. So, we multiply we have, so we squared the z. So, 1 square, and this is a, because this is 1 we have to multiply. So, this is this, then again Bi is 1. So, again we squared this z, now z is this one. Now, again we squared z and then we multiply with a, we got this, and every time it has to be mod n. So, every operation is under mod n. So, this into this mod n will give us this. So, now Bi is 0. So, we do not need to multiply, we just square it, the z. So, if you square this z, it will be this square, then mod this will give us this. So, this way we will continue. Finally, we got this 5761 as the result, that z. So, this 5761 is basically m to the power 9726 to the power 3533 mod 11413. Okay. So, this is called square and multiply method. So, every time we square z, and once we have a, once we see a 1 we just multiply. Okay. So, this method has a problem in terms of what is called side channel attack. So, it is a side channel attack. So, we will talk about this attack in more general when we will discuss the cryptanalysis. So, for the time being, suppose this is Alice and this is Bob, okay. And suppose Bob received this y to be this number a, say 9726, okay. And say Bob's secret is, say d is equal to say this m 3533, okay. This is the secret of Bob. This is our m in our square and multiply method, and this is our a in our square and multiply method. And so, now Bob need to calculate, this is the m which is the secret key of Bob. Now, Bob need to calculate a to the power m mod n, and suppose n is in the we are taking the example that we have seen 11413, okay. So, suppose in Bob's machine, Bob is calculating this using the method just now we have described, this one, that square and multiply method. So, Bob is having this secret key and Bob is receiving this ciphertext. Now, Bob need to calculate this in order to get the message back. So, this is suppose the plain text. So, if Bob calculates this algorithm, if Bob execute this algorithm in Bob machine, so then suppose Oscar is sitting in the side of Bob machine. Suppose Oscar is sitting here, Oscar is sitting here, and Oscar is just watching the Bob machine's functionality. Okay. So, in the Bob's machine this code is running, this calculation is going on. Now, Oscar is sitting, Oscar will see, Oscar knows that the Bob is using the square and multiply method. So, Oscar knows that every time it is squaring and multiplication will be done except once these bits are 1. So, Oscar will check the timing, how much time it is taking in the Bob's machine or how much power consumption it is doing. When Oscar will see the some loops, the power consumption, this is basically a loop, for loop. We have seen this algo as a for loop. So, this is the for loop, it is starting from this. So, this is basically for loop. So, Oscar will just see in this for loop, if it is square it will take similar time, but if it has to multiply. So, this operation square and multiply, then the corresponding BI must be 1. So, that measurements Oscar can either by seeing the timing or the power consumption, because more operation means more power consumption. So, in the Bob's machine Oscar can fit a machine to measure the temperature or to measure the time. So, then by seeing this how much time it is taking, suddenly Oscar see in some loops in some BL, say for some loop, this is a loop from k down to 1, and then we are doing every time squaring and sometimes we are multiplying if BI is 1. So, suppose for L I is equal to L, I is equal to 10, Oscar is saying it is taking more time, that means corresponding B10 must be 1. Okay. So, Oscar will just measure the, by sitting side, Oscar will just measure the time of the computation by either putting some machine like the power machine or something. So, this is also called timing attack. So, then Oscar will guess these bits are 1 basically, because this is taking more time, because it is doing one more operation, multiplying operation. So, then Oscar can guess these bits, this is 1 1 1 like this. So, this is called side channel attack. We will talk about this on more details when we talk about the cryptanalysis. Okay. So, this is this square and multiply method has a drawback. Okay. Now, we will talk about another aspect of computation complexity of RSA, which is called key generation. So, for key generation we need to have a prime number PQ, which is, and we compute n is equal to PQ and we are making n to be public. So, this means the RSA security is based on the factorization is hard. So, if you choose say n is say 27, sorry 21, then this one can easily guess that p is equal to 3, q is equal to 7. Okay. So, then it is not secure, because once we know the PQ, then we know phi n, then one can guess the E is known. So, one can guess the D. Okay. So, now, so that is why we cannot take n to be so low number. So, you have to choose n to be large number. In order to be n to be large number, then PQ to be large. So, we need to have 2 prime number PQ. So, these to be large prime. Okay. So, for key generation we need to have a prime number, not only prime, large prime, say 512 bit prime. Now, the question is where from we can get this prime. So, that is one issue of computational complexity, how to get a prime. Suppose Bob needs a 512 bit prime. Okay. So, Bob need a Q, PQ, which is 512 bit, 01 bits. So, now the question is there any algorithm which can give us this prime, I mean 512 bit prime or any bit. So, we will give the input L bit and we can ask give me a prime, give me a prime of L bit. So, is there any algo which can do that? Is there any machine or is there any algo which can give us, we give the input 512, give me a prime number of 512 bit. No, there is no such algorithm exists in the literature which can give us a prime number. So, what we can do? We can test the, we can do the primality test. We can choose a odd integer, then we can test whether this is a prime or not. So, those are called primality test. So, basically we can give an odd integer n of L bits say, and then this algo can tell us whether n is prime or not, prime or not. Okay. So, suppose I ask you, is the number 7 is prime? So, a number is when we say number is prime, a number is prime if it has only two divisor, G1 and itself, then we call the number to be prime. So, if n is prime, so that means n has only two divisor, 1 and n itself. So, that means there is no other divisor of n. So, now how to test 7 is a prime? So, if you want to test 7 whether it is prime or not. So, 7 is prime. So, how to test that? So, that means we want to check whether the 7 has any factor or not other than 1 and 7. So, that means we have to check whether 2, 3, 4, 5, 6 this divides 7s or not. So, if we can check that, then we are done. So, no numbers divide 7. So, that means 7 is a prime. So, if instead of 7 if we have some big number like n. So, do we need to go up to 6 or we can just go to the square root of 7. So, this method we can go up to the by checking square root of n to check n to be prime. So, we can go this method a is less than equal to up to square root of n. Why? Because if n is has a factor, if n has a factor which is greater than, if n has a divisor greater than square root of n, which is say a, then so n will be written as a into b. So, a is a divisor. So, b is another factor. So, then b must be, b is equal to n by a. Now, so then b must be less than square root of n. So, that means if n is not a prime, then there has to be a divisor which is less than square root of n. So, for this checking we do not need to go for up to 6, we can go for up to square root of 7. So, that means square root of 7 is 2. So, we can just check whether 2 divides 7 or not. Okay. So, this is a naive approach, this is work perfectly fine, this is a deterministic approach. So, this way we can tell a number is prime or not. So, problem with this method is if n is big number, suppose n is say 10 to the power 100, then square root of n is basically 10 to the power 50. So, up to this much number we have to check for finding the this is prime. So, this is not a very efficient method to check whether n is prime or not. So, another approach could be the sieve. Okay, this is the sieve approach. So, the idea is, so we want to test whether n is prime or not. Okay. This is sieve Eratosthenes. So, this is basically to test whether n is, the idea is, so we consider all the numbers from 0 to n and then we remove all the composite numbers, and then slowly the remaining number is basically the prime numbers. So, the idea is we just take all the numbers say from 1 to n and then we remove all the composite number like this way. We first remove all the number which is multiplying by, which is the which is basically multiple of 2, multiple of 2. Then we remove all the number which are multiple of 3. Multiple of 2 means 2, 4, 8, 4, 6, 8, 10 like this. Then we remove all the number which are multiple of 3 and which is not removed by 2. So, this is basically 9, 15, 21 and so on. Then we remove all the number which are multiple of 4, but that is covered under 2 multiple of 2. So, we remove all the number multiple of 5, 45 like this. So, this way we continue up to root n, because we are checking. So, this way we can just removing all the numbers which are composite. So, that means if we just take n is equal to 100. So, 1, 2, 3, 4, 10, 11, 12, 20 like this, then 90, 91, 92 like this, 99. So, now first we remove, if we start from 0 and 1, we remove 0 and 1, then we remove all the number multiple of 2 like this, then we remove all the number multiple of 3 like this, then this way we continue up to square root of 100. Then the remaining number left out in this table is the prime number, but this method is also not so efficient, because if n is large, this way the removing the composite is not so efficient idea. So, now there are some probabilistic approach. So, these are all deterministic approach. Now, there are some probabilistic method to test the primality test. So, those are probabilistic approach. So, it may give us the prime number, may not. So, the success probability is there. So, those tests are basically Euler's test, then Solov's Stresson's test. We will see some of the test in our future talk, and then the Miller-Rubin test, and maybe some more tests, but those are all probabilistic tests, not the deterministic test. So, now we can, so these are the tests we have to run. So, this is basically summary of key generation for the prime. So, we pick an odd integer, and then we have to perform the probabilistic primality test, like we can use the Miller-Rubin test, and if we false, then we have to choose the another, we have to try for another number. So, these are all to generate the primes. So, then so now come to the, so this is the way how we can generate the prime. Now, come to the RSA security of the of this crypto system. How RSA is secured, why RSA is secured. So, RSA is based on the factorization is hard. So, that means n is public, p of, so n is some pq we know, but only thing we should not able to factor it. So, that factorization must be hard. So, for this purpose we can try to factorize. So, these are the attacks on RSA, like brute force attack, mathematical attack, timing attack. So, timing attack means that square and multiply, we have seen some side channel attack. So, for brute force attack, so these are the parameter RSA should have in order to be secure. So, this the numbers are basically key size are this many bits for our applications, like if military application we need to have the key size should be this. So, our prime number should be this many bits, which is very challenging to get this many bits prime number. So, these are under brute force method. So, there are some mathematical methods. So, this is the best known method for poloid is one method for doing the factorization. This is the best method for doing the factorization, this time complexity. So, and then we have seen the timing attack. So, timing attack is basically we have seen the if Oscar is sitting in front of the Bob's machine, and if Bob is doing the square and multiply method for calculating exponent, then Oscar can guess the key. Okay, thank you.